Actual definition of your pH and the pOH. pH is this, pOH is this. So you can see the pH is calculate your proton concentration, and then your pOH calculate the hydroxide concentration. And the only things make it become pH or pOH is simply because you take a negative log. If you know the proton concentration or the hydroxide concentration at equilibrium, then you can calculate the pH and the pOH of your solution. So one thing that's very important is that these things has to be at equilibrium, because only under that situation your pH will be a constant value. We are going to use water as example to calculate the pH. So what's the pH of water? 7 at what temperature? Yes, 25 degrees C. So every time we say the pH of water is 7, that is only true when your temperature is at 25 degrees C. Otherwise, your pH of water will vary. What we're going to do now is actually going to show you that. So this is the chemical equation of water. Water is going to dissociate into proton and the hydroxide. At 25 degrees C, your Kw or Keq is going to equal to 10 to the negative 14. Then we want to calculate the proton concentration and the hydroxide concentration at equilibrium. So what is the concentration of water? That's actually the things I wrote here. That is the concentration of water. It's actually very high in concentration. Then we are going to use our ice table to find out what's the concentration of my proton and the hydroxide, right? Because the K is so small, right? We assume everything actually exists in the reactant form. So the concentration is 55.56, assuming it haven't dissociated. Small portions of water is going to dissociate. It's going to produce your protons, produce your hydroxide. And then we are going to reach equilibrium. So we have 55.56 minus X for your H2O liquid, X for your H plus, OH for your OH minus. So next one is actually I'm going to apply the KEQ to actually get your X. So here the things you want to be careful is that when you write out your equilibrium equations, you can see here I only put H plus and OH minus. And the main reason is because the pure liquid did not go into your equation. This is what you're going to write. Okay, so let's actually X times X. X squared equals to 10 to the negative 14. So the X is going to equal to 10 to the negative 7. And then that's going to tell us that your proton concentration is going to equal to your hydroxide concentration. That's equals to 10 to the negative 7 m. So once you know the proton concentration, once you know your hydroxide concentration, if you take the negative log of that gives you the pH and the pOH, which is actually the things I wrote here. Okay, so your pH is going to equal to 7. Your pOH is also equals to 7. It means actually you have equal amount of protons and hydroxides coexisting inside your solution. But the concentration of those things is actually very low. Okay, so they're actually very far away from each other. They don't actually feel each other. All right, so one very important concept you should know is actually this alpha. Okay, alpha is called the percent dissociation of the species you're actually working on. Okay, so in this case, it will be actually the percent dissociation of water. It was defined as the proton concentration over your reactant concentration times 100%. In homework, they will ask you, okay, what is the percent dissociation of a certain species? Okay, and that's the equation you're going to use. So if you do this, your proton concentration is 10 to the negative 7. And then your water concentration is 55.56. So if you do that calculation, you can see that only 1.8 times 10 to the negative 7% of your water will dissociate into H plus and OH minus. Very, very small amount. Okay, with all this calculation, we have this table, right? We know the temperature at 25 degrees C, the concentration of proton is 10 to the negative 7, pH is actually 7 for your water. pH is actually 7, right? Proton concentration is that, okay? Your pKw, okay, which is this guy. Take the negative log of 10 to the negative 14, that give you 14 here. That's your alpha, okay, that's your Kw. Everything is actually at 25 degrees C. Now, if I ask you, if right now I increase the temperature of the reaction, how these values I highlighted here will change. To answer these things, first things we need to actually see this equation more carefully. H2O, let dissociate into H plus and OH minus, and the delta H is equals to 56 kilojoules per mole. What does this mean? Is this reaction endothermic or exothermic? Endothermic, right? When you say endothermic, that means actually need to heat up the system so the reaction will move to the right. Right now, we're actually comparing the temperature at 25 degrees C. So think about this. If I increase my temperature, okay, larger than 25 degrees C, how would actually affect your proton concentration? It is an endothermic reaction, right? That means actually if you increase the temperature of your reaction, the reaction is going to move to the product side, which is the side that contains your proton and the hydroxide. If the temperature is actually larger than 25 degrees C, would you expect your proton concentration to increase or decrease? Increase, right? So you know, this thing is going to increase, okay? It's going to be larger than 10 to the negative 7 N. Right now you have proton concentration larger than 10 to the negative 7. If I say, that is my proton concentration. pH is actually, if you take the negative log of this, what do you get? 5, right? So you know, if you have a larger than 10 to the negative 7, your pH is going to smaller than 7. How about your alpha? Does your alpha increase or decrease if you go to higher temperature? Alpha is actually the proton concentration over your H2O concentration, right? You're going to have more protons inside your solution. Therefore, your alpha is going to increase. Your Kw is actually the product of your proton concentration and your hydroxide concentration. They are the same amount. So if you go to higher concentration, what happened to your Kw? Increase is actually 10 to the negative 5, right? Your Kw is actually the square of that. That's actually 10 to the negative 10. So is that increase or decrease? Increase, right? How about your pKw? It's going to be 14 or smaller than 14. Smaller than 14, right? So that's actually the things that you have if the temperature increase. Okay, and then all these parameters will change accordingly. If you go to a temperature that's actually less than 25 degrees C, it's the opposite. Okay, so this will decrease, larger than 14, smaller than 10 to the negative 7. This will be larger than 7. One last question. If I go to this case, if I measure the pH of water higher than 25 degrees C, I got a pH value that's smaller than 7. Is the water acidic, basic, or neutral? So if you go home, ask your mom, okay, Mom, is water acidic, basic, or neutral? What would your mom tell you? Neutral, right? So what does this mean? What it means is just like, okay, it actually represents the concentration of your proton. It doesn't change the nature of your water. Your water will still be neutral because you have the same amount of proton and the OH minus, right? You have increased the proton concentration, but at the same time, you also increase your hydroxide concentration, right? They will still cancel each other. They are still neutral. Even if you see the pH is below 7. So if you actually go to different temperature, the neutral value of your pH also changes. No, regardless of temperature, your water will always be neutral. Okay, the pH just tell you quantitatively how much protons you have inside your solution. I hope this gives you a good soft exercise about how you actually can calculate the proton concentration in the aqueous solution. Okay, and you should also realize that the pH smaller than 7 is not necessarily equals to the solution is actually acidic. Okay.